Thanks for making this talk. So I'm going to talk about a couple of things. So the importance of getting the abstraction right and software engineering. So the importance of having a solid, robust software engineering culture. So I'm going to use DeVito as an example because we as a company have been developing DeVito for 7 years. Obviously, but most importantly because, so there's a myth. So a myth is that, the myth is that, so DeVito has grown in popularity because it can run fast on many different architectures. What we claim is that that's just a consequence, that's just the natural consequence of something else, of something way more important, which is this guy here at the top. So getting the abstraction right at all possible levels. That's really the key, the most important thing we've done and that we still do. All right, so this is just to, some probably stuff that you all know about, but some context. So seismic imaging is challenging for all sorts of reasons. Well, you have to think about the imaging algorithms themselves. You have I/O, you have pre-processing, post-processing, gradient stacking, and all sorts of things. And possibly on a different axis, you have to deal with HPC. Because virtually for all of these things, you have to think about efficiency for obvious reasons. And inherently to this fact is, so HPC, you have to think about HPC and the fact that it's multi-level parallelism. So you have to think, for example, about parallelism at the level of the shots, parallelism at the level of the wave equation, and so on and so forth. So these all together contributes to the complexity of our ecosystem. And I shall add that what makes this field particularly, so at the same time, fun and fascinating is the fact that to deal with most of these things, you need multidisciplinary knowledge, which means that you are either a polymath, or you work with polymaths, or you have to talk with people with background and expertise different than yours, which is, in my opinion, extremely rewarding, fun, and well, it's not just typical of seismic imaging per se, if we want to be completely honest. It's more about, computational science tends to have this, but, So that said, and now focusing on the wave equation, because that's what we got at the core of each of these algorithms. So, okay, so first of all, it's not just the wave equation, unfortunately. There are many incarnations of the wave equations, and obviously some are way more challenging than others. And on one hand, you have the mathematical problems. So for example, you have to deal with stability. On the other hand, you have the HPC, because all the implementations of whatever incarnation of the wave equation have to be as efficient as possible. So what this means is that people write code bases, and over the years, the code bases become more and more complex. So more and more performance optimizations are added, meaning that the codes tend to get more and more impenetrable. So this contributes to complexity, to the challenges with maintenance, and so on and so forth. When you have to port an implementation to another architecture, then the complexity blows up, or at least it increases significantly, because now, unless you have proper abstractions in place, you have to, you have to deal with multiple implementations, even for one just type of wave equation. And some people are perfectly fine with that, and maybe, that makes complete sense to me, in a sense. There are like companies, like teams, they've got people who have done solvers for the wave equations for years. They've got those solvers, they run them in production, they run fast, it's all good. That's absolutely fantastic, but not for everyone, not for everyone. And maybe what is true today doesn't have to be true tomorrow for a number of reasons, but most importantly, for this thing here. And so the core issue is the fact that the implementation space is huge. So especially now, more than yesterday with the entire world transitioning towards elastic solvers with, for example, a high frequency elastic FWI. And on different axes, you have to think about, I don't know, the type of media within which the waves propagate, attenuation, and last but not least, the fact that these codes need to be somehow platform portable. So these are all different axes which contributes to the combinatorial explosion of the problem. So all this introduction to motivate why years ago we did this thing. So we wanted to do HPC for Seismic, and we started writing monolithic solvers. And then early on, we were going to conferences, talking to people, telling us that they have all sorts of wave equations that they need to run on CPUs and GPUs. And so we saw immediately that what we were doing wasn't going to scale. So we decoupled. So we say, let's decouple the mathematics from the low-level implementation. How do you do that? That's a classic computer science problem. You introduce a new level of abstraction. So that's why we came up with this domain-specific language, which for those of you who are not familiar with the DeVito DSL, you can see that there's a fairly close relationship between the terms of the DSL and the terms of the partial differential equation at the top. So for example, here I'm taking the Laplacian of the wave field, which you see here, and here I'm taking the second order time derivative, which you see here. So the DSL, which by the way is built on top of an extremely popular mathematical package called SymPy, allows the geoscientists to finally focus on their job, on their science. They don't need to care about the HPC, about the low-level implementation. They don't need to care about parallelism, because it's all hidden away. All they do is focusing on the mathematics and the geoscience. Clearly, we haven't invented the DSLs. In fact, what we did, so I and Gerard come from Imperial College. For those of you who don't know, Imperial College is like one of the cradles of DSL technology. I did my PhD at Imperial. I was working on DSLs for finite elements, learned all sorts of things there, made all sorts of mistakes. We took all of that and built this DSL, which was the first game changer. So we got 7/8 years ago, we decided to do that, and that was the first game changer, but not the only one. But that, at least, like with that move, we were starting to get the abstraction right, because we were placing maths at the top. And so, okay, so just very quickly, as I said, so the DSLs are, in our case at least, for decoupling mathematics from HPC, and to achieve altogether productivity, portability, and performance. And the paradigm, basically, is that like the contract between us, developers, and the user is that you write the code once, or the mathematics once, if you want, and that code is going to run everywhere. Many DSLs have failed, not just in our field, but more generally in computational, in the entire field of computational science, for a number of reasons, including software engineering, the lack of a proper software engineering culture, or maybe simply the fact that most of these projects, they come from academia. Academia, in my opinion, is totally broken, because you have to basically cope with this issue here. And so just they tend to fail over time. And that's one side of the story. The other side of the story is exactly what I said earlier. So many DSLs tend to provide an API which is way lower level than the mathematics. And if I show this API to geophysicists who want to do the science, I'm not going to breach through them. Because sure, maybe you give them performance, but you are not giving them high productivity. And if you have a huge code base and you want to port that code base to something new, you need incentives. And an incentive is to be able to be as performant as highly productive, which is what mathematics gives you. Now, this is another example of why it matters so much to get the abstraction right. So when we were giving our first DeVito talks, like 7 years ago, more or less, one of the questions that we were getting at the end of each of our talk was, okay, fine, we get it. You have a mathematical language to solve partial differential equations, and that's fine. You can even solve Navier-Stokes with it. It's not limited to the wave equation. That's all beautiful, but what do you do with boundary conditions? Because boundary conditions are an absolute nightmare. There are all sorts of boundary conditions. And those questions made us think pretty hard about what to do next. Because an obvious move at that point was, oh, okay, we are just going to provide an API for each boundary conditions. But that was not going to work. And we saw that immediately. Because there's always someone that wants to do something special. There are boundary conditions that escape the textbooks, okay? So there's always something special that people want to do and try and so on and so forth. So what we realized is that at the end of the day, what we had back then was a mathematical language for finite differences. But with some little tweaks here and there and some generalization, we could have used that same mathematical language to actually express generic mathematical operators, to do inner products, for example, or to express generic boundary conditions, because boundary conditions are just a piece of mathematics, if you want. So we do this generalization effort. It was a bloodbath. It took us some time. Then we coupled it with another API. It's the so-called subdomain API, which allows the user to define subregions within the physical domain. And so now you can define regions within a physical domain. So for example, you can say that here at the top, I want free surface. You have the mathematics. I'm going to use the mathematics to implement my own formulation of free surface in this specific region of my physical domain. So it's through this flexibility, and you only get this flexibility because you got the abstraction at the right level, that we could allow people to do whatever they wanted, to, for example, replicate what they had in-house through DeVito. And so the concept is that what we are providing is a toolbox for developing, creating whatever kind of mathematics you want. And nothing is pre-baked. So this applies to solving the partial differential equations, to the boundary conditions, but also to other stuff, like to the imaging conditions, so to like everything that you need for scaling these solvers, even at production level. And okay, so here's, I mean, all of that is fantastic. It's, I mean, we need the abstractions, the right level, and abstraction. I mean, if it's too high level, it's not going to be flexible enough. If it's too low level, it gets too tricky to get used and to make a breach through the community. None of that matters if you don't have a solid software engineering culture, meaning that you want to have high quality code, of course. More importantly, you want to have solid, rigorous testing. Ideally, you want to have as much code for testing, as much code for whatever you are doing. Continuous integration is crucial, continuous deployment, and containers, which I decided to put here at the bottom because in our community, as I said earlier, at the end of the day, we want to be performance portable. We want to be able to run on all sorts of architectures. And if you don't use some form of virtualization, meaning like containers, for example, together with continuous deployment, it's just going to be a nightmare to test and validate and verify your codes. So these are all crucial. And then the other thing that I wanted to say is that what really worked well for us, or at least for me, because when I started at Vita, I was a postdoc at Imperial College, and I had Gerard there. He was like my manager at the time, and he wasn't like pressing me, like pushing hard on me to deliver features as quickly as possible, because we want to have an impact on the industry. On the other hand, he gave me, well, us, the entire team, the time to do this thing here, writing tests. So we were adding functionalities, and then we were writing tests, adding functionalities, and then writing tests, and then doing that, and then adding them to continuous integration. So it's through this cycle that we got to this point. If you let this culture, the must be ready yesterday culture, eat you alive, then your software is not going to survive. Or maybe it does, because you have a company behind you throwing a lot of money at you, and so you have a team full of people to write and maintain the code, but it's going to be massively painful. So try to break this loop. So, and this is just a case study. It's like putting together all the things that I've mentioned so far. You can do some pretty beautiful things. So here you have some mathematics, the Vito, through which you can write, you can express solvers for whatever wave equation. And then by coupling that with other state-of-the-art technologies, for example, GitHub Actions to automate deployment, and Docker to essentially containerize your application, which makes it absolutely fundamental to be able to run it on different CPUs and GPUs, and you just don't go crazy when the next GPU comes to the market. All you have to do is, well, maybe tweaking the container a little bit, but possibly just building an image on that new architecture, and then the code just runs. So it's by chaining together all these things, we have created a pipeline that basically translates mathematics into HPC all automatically. It's now as difficult as pressing a button through the GitHub Actions interface for us to implement one of the most important features in our field, which is performance regression. So you develop a new feature, and then a new feature, and then another feature, and then there's a new version of GCC coming out, and then there's a new SDK. So things evolve over the months, and then at some point you want to sync and make a checkpoint of your performance. You need a performance regression system. So by pipelining together all these things, we press a button, run a set of benchmarks on all of these architectures, CPUs, GPUs, from all vendors, and then at the end, we deploy, so like what you can think of as performance tables. On each row, you have an architecture, and I'm done. I went super quickly. On each row, you have an architecture, and here in the columns, you may have, for example, the absolute performance of these benchmarks in terms of gigapoints per second. Or if you care about cloud, you can think of other metrics like price performance, for example, and so on and so forth. So this is, for example, what we can create in a fully automated fashion today. So this is an example of performance regression. So basically, this line here aggregates the gigapoint per second performance across all our benchmarks, across all of the architectures we run on, GPU architectures we run on. And these show the evolution of performance over a period of 1 year. And you see that it tends to monotonically increase. It lacks some points here, between here and here, because we were doing some other stuff. But now it's being resurrected, so we have this framework which is now alive. so we can use it, and so we can create these pictures, these plots, to one, convince ourselves that we haven't broken anything, and two, convince the user or prospect that we are honoring our promise, which is basically sit back, relax, write the mathematics, you are going to get some performance. This performance is going to improve without you having to do much, except maybe for some tuning. Clearly, this is all aggregated, but we internally have the data points for each architecture and benchmark, obviously. That concludes my talk. So basically, the takeaway message is that at the end of the day, we are here to accelerate geophysics. And for me, the most important thing is getting the abstraction right. We've done that at the beginning. We are doing it today. Geophysicists, they want to be doing, they want to do geophysics. They want to do mathematics, don't want to do HPC. And so we are trying to make them happy, basically.
Okay, but we probably have time for one or two questions. Michael?
You mentioned different hardware targets, CPU and GPU. Do you do any optimization or tuning per different hardware target?
Yes. So basically, what we've done over the last 7 years was working in parallel on one hand on the APIs and the abstractions, and also especially because we are a multidisciplinary team. So we have the geophysicists that, like Matthias and Ed in this case. So together we devise the abstractions, but we also have spent a huge amount of time on implementing the right compiler optimizations to generate code which is as efficient as possible on CPUs and GPUs. So we do classic stuff as well as more exotic things depending on the specific architecture.
Can you say a few words? How did you optimize per specific architecture or CPU versus GPU? Do you take a few kernels, you compile and run, generate C code, I guess, then you compile and run, and then you go back and change the source code that you generate, or what is your app?
Oh, well, it's our compiler. So at the end of the day, we are building a compiler that translates the DSL into code. And what we do, like month after month, we improve the technology inside the compiler to generate code which is better and better, which gets better and better. Yes, so we do that. So for example, whatever PDE, we want to make it faster, so we generate the code, we run it through a profiler, we see that there's room for improvement if we did that. So we try like some manual modification. Okay. So we learn from that experience, and then we translate that knowledge into the compiler. So that's typically our workflow, with the caveat that we are performance portable. So we need to be sure that either that optimization works well on all possible architectures, or it only works very well on that specific architecture. So we have to do that study, that analysis, to make sure that what is an optimization for architecture A isn't actually the source of performance degradation for architecture B.
Do you have any tool to go through the results and provide you some feedback? Okay, based on this architecture, or is just manual process? No, looking at
we use the like state-of-the-art profilers from each of the vendors, like Insight Compute from NVIDIA, VTune from Intel,
okay.
and
yeah, and I understand. I was referring to if you use some, for instance, machine learning tool to go over the results and then provide you some suggestions.
No, this is all good old-fashioned HPC.
Good old-fashioned. Okay, thank you. Thanks.